It began as a whisper against the darkness, a faint tremor of reflected light moving through the deep, unlit corridors between the stars. Before it had a name, before catalogue numbers and orbital solutions and frantic telescope shifts, astronomers spoke of it the way ancient sailors whispered about distant lanterns on a black horizon. Something had entered the solar system from a direction no familiar pattern predicted crossing the boundary between our sun's dominion and the open interstellar gulf with the quiet determination of a traveller shaped by foreign physics. Later, it would earn the designation 3I Atlas, the third confirmed object from another star system ever seen passing through ours. But in these first moments, it was only a silhouette with a story locked beneath its dust. Its arrival was not heralded by the luminous spectacle of a comet flaunting its icy tail. Instead, it moved like a modest wanderer, dim and unassuming, almost deliberately restrained, as though hiding its origin from those who would eventually chase it with the sharpest instruments humanity had ever built. And yet something in its trajectory, something in the way it carved through the gravitational fields it touched, suggested age endurance, and a journey measured not in centuries but in millions of years. It came from a place where the sun is merely one more pale dot in a sea of cold fire. The mystery did not begin with its motion. It began with its silence. No radio emission, no flaring cry of evaporating ices, no sudden brightness as it neared the warmth of the inner planets. A body travelling through the emptiness between stellar nurseries should have been stripped bare long before reaching us bleached to stone by cosmic rays and interstellar winds. And yet Webb, when its gaze finally settled upon the faint traveller, found the opposite wisps around the object traces of materials far too delicate to survive such an odyssey, without protection or replenishment. Something clung to it. Something followed it. Something that should not have endured. In the opening observations, scientists described a halo that wasn't a halo, and a tail that behaved like no comet's tail known to science. Around 3I Atlas, Webb detected signatures that shimmered with contradiction. A veil of matter, whose spectral fingerprints hinted at chemical balances startlingly out of place. It was as though the object carried a memory of the environment that formed it, an environment far different from the sun's realm. Dust grains with mismatched structures drifted near it, too pristine for their age, too abundant for their expected loss, too diverse for any simple explanation. And behind that contradiction lingered a more unsettling question. Were these materials being shed by the visitor or drawn toward it? The universe has always offered humanity mysteries, black holes swallowing starlight neutron stars spinning like cosmic lighthouses, galaxies colliding in slow gravitational dances. But this was something else, a puzzle moving directly through our cosmic neighbourhood, close enough to be measured, tracked, dissected with instruments designed to read the faintest secrets in starlight. And for the first time in history, humanity possessed a telescope with the sensitivity to examine an interstellar body not merely as a point of light, but as a textured, evolving system. The James Webb Space Telescope, orbiting far beyond the distortions of Earth's atmosphere, carried infrared eyes capable of pulling whispers from the vacuum. As the faint wanderer approached the sun's gravitational domain, its story unfurled like a slow, deliberate revelation. Scientists prepared protocols for observing something that did not belong to our world, adjusting exposure, times, shifting target priorities, and testing the limits of Webb's spectrographs. Even then, the first data that flowed back through the deep space network carried a weight that no one expected. What Webb detected around 3I Atlas suggested not a passive drifting relic of another star system, but a body engaged in processes still active, still evolving, as though it had not yet surrendered to the entropy of interstellar travel. The anomaly around it was faint but persistent. Certain wavelengths brightened where they should have dimmed. Patterns appeared where thermal models predicted smooth, featureless profiles. Infrared signatures emerged that matched no simple mix of rock, water ice, and organic compounds. For a moment, just a moment, the scientific world held its breath, not because the object appeared artificial or engineered, but because it seemed to be obeying rules that did not align cleanly with the well-mapped behaviours of comets or asteroids formed within our own solar system. The deeper the analysis reached, the more it suggested that this visitor carried secrets buried within it, secrets of a different protoplanetary disk, of a different stage of cosmic evolution, perhaps even of a star long extinguished. The possibility that its material composition encoded a chemical history billions of years older than Earth gave the object a solemn, almost sacred aura. It was not merely a rock from somewhere beyond Orion or Cassiopeia, it was a shard of a forgotten birthplace drifting into our sky. And yet beneath the beauty of that idea lived something colder, something the data would force astronomers to confront. For among the faint signals Webb recorded were irregularities that defied expectations, inconsistencies that refused to resolve into the clean lines of known physics. The haloing material did not expand as solar heating increased. Some emissions brightened before the object came close enough for temperature to be the cause. Certain dust grains seemed to accelerate outward, while others clung tightly locked in place by forces that calculations insisted were too weak to hold them. Webb had seen something around 3I Atlas that resisted every template astronomers attempted to apply. And although the initial findings were quiet, almost cautious, the sense of unease grew. In time, these first spectral whispers would ignite a scientific firestorm, one that would reshape the questions humanity asks about interstellar travellers, their origins and the unseen processes that govern them. As 3I Atlas moved silently through the solar system, carrying its unknown halo and its mismatched chemistry, it left behind a wake of fascination and apprehension. The scientific community understood that this journey was fleeting. Gravity would soon pull the object onward back into the dark ocean between stars. There would be no second chance. Whatever Webb detected, whatever story lay hidden in the anomaly drifting around this visitor, would have to be captured now before the wanderer slipped once again into the abyss. The mystery had arrived, and Webb, with its ancient light-reading mirror of gold and shadow, was listening. Long before the anomaly ignited debate, before spectral lines twisted into riddles, there was only the discovery itself, quiet, almost routine. It began with the asteroid terrestrial impact last alert system, Atlas, scanning the sky from Hawaii, its automated algorithms sifting through the persistent churn of faint streaks and wandering dots that populate nightly surveys. Most detections belong to familiar families, near-Earth objects meandering through predictable ellipses, dormant comets, tracing ancient paths, fragments of primordial collisions wandering like debris carried by the solar wind. But in late 2022, Atlas flagged a dim, slow-moving object that drifted with a peculiar slant across the sky. It did not match the established maps. Its motion, subtle but undeniable, possessed the mathematical fingerprint of a hyperbolic orbit, a trajectory not bound to the Sun but slicing past it on a one-time passage. Initial orbital solutions were crude, but even in their roughness they hinted at something extraordinary. The object was not falling inward like a returning comet. It was simply passing through. This was not the first interstellar visitor humanity had glimpsed. Oumuamua and 2I Borisov had opened the door to this new domain of cosmic archaeology. Yet every object from another star system carries its own accent, its own chemical signature and dynamical history, and this new body, soon labelled 3I Atlas, arrived as a puzzle whose edges did not yet fit. Observatories worldwide pivoted to capture better data. The Pan-STARRS telescopes weighed in next, refining its arc. Then the European Southern Observatory, the Canada-France-Hawaii telescope, and a constellation of smaller instruments aligned their sightlines toward the dim drifting speck. But discovery is more than measurement. It is context. Astronomers attempted to reconstruct the object's past, tracing its path backward through the tapestry of the galaxy. Doing so required threading its motion through the gravitational fields of the planets the Sun, and even the minute effects of radiation pressure. Early attempts were inconclusive. Unlike Oumuamua with its sharp deflection, or Borisov with its clean cometary signature 3I Atlas left fainter clues. Its path through interstellar space was harder to model, its incoming velocity modest yet undeniably foreign. The Sun had not birthed it. No gravitational dance within our planetary system could explain its momentum. Speculation emerged about its point of origin. Perhaps it had been ejected from a young star system undergoing violent planetary rearrangements. Or perhaps it had drifted for eons, expelled from a dying star's debris disk, bearing ancient material forged when the cosmos was younger, when metal content in the galaxy had been lower and chemical bonds arranged themselves differently under colder suns. But without direct sampling or spectroscopic scrutiny, these were only sketches drawn in the dark. The turning point came when infrared observatories added their perspective. The NEOWISE mission, designed to detect the faint thermal glow of objects too dark for optical systems, confirmed that 3I Atlas reflected little sunlight and radiated even less heat than expected. Its surface appeared cold, inert, and muted. Early compositional guesses leaned toward a rocky or carbon-rich body, something that had endured long exposure to cosmic rays. Yet small brightness fluctuations hinted at irregular forms, perhaps protrusions or fractured surfaces rotating slowly. The object was moving steadily toward the inner system, though not deeply enough to promise dramatic brightening. Its closest approach would be distant, a mere brush along the outskirts of planetary orbits. But the prospect of observing a third interstellar object stirred a seriousness in the astronomical community. Webb's mission planners received their first inquiries. Could the telescope spare time to capture spectra of a faint, fast-moving target? The possibility remained uncertain. Webb's observational schedule was meticulously choreographed, crafted months in advance. Shifting its attention required scientific justification and technical feasibility. Yet interest intensified when the Las Cumbres Observatory's global network captured subtle hints of activity, barely perceptible deviations in luminosity that could in the best interpretation signal faint outgassing. A vapor jet perhaps, or thermal shedding of surface molecules as the object felt the distant warmth of the sun. It was not enough to classify it as a comet, but not so negligible as to be ignored. Something was happening on its surface, something more dynamic than a silent ancient rock passing through. The prospect of activity on an interstellar object electrified researchers. Borisov had behaved like a comet. Oumuamua had famously behaved like neither rock nor ice, igniting fierce debate about outgassing without visible emissions. If 3i Atlas carried even the faintest traces of sublimation, it became an invaluable glimpse into chemistry forged beneath an alien sun. Such material, if detected, would serve as a direct sample of chemistry, beyond the solar system clues to different planetary formation pathways, different cosmic environments, perhaps even different heat histories. By the time the Minor Planet Center finalized the official designation of 3i Atlas, observatories across the world had committed significant resources to tracking it. Radar was ruled out too distant, too small, too dim. But spectroscopy was within reach. The Keck Observatory attempted the first high-resolution spectral scans, though the object's faintness and atmospheric distortions limited the clarity of the results. Through all of this, a slow shift began in the astronomical community, a growing sense that this object deserved Webb's attention not as a novelty, but as a scientific opportunity unparalleled in its potential. Humanity had only just begun the study of interstellar wanderers. Each new visitor could redefine models of star system evolution. Webb's infrared reach spanning wavelengths inaccessible to ground-based telescopes made it the perfect instrument for reading the chemical and thermal story of the object. In late planning sessions, researchers prepared proposals emphasizing the unique chance presented by 3i Atlas. They argued that Webb might detect subtle spectral lines corresponding to ices that had survived interstellar travel or refractive dust grains formed in environments unfamiliar to us. The question underlying every submitted request was simple. What was this object made of, and how had it endured the brutal voyage between stars? The answer would soon surpass every prediction. When Webb's time was granted limited, carefully scheduled but sufficient, the stage was set. The telescope turned its golden mirror toward the faint signal drifting through the dark. The first photons, ancient by the time they reached Webb's detectors, carried the truth of the object's surface and its surroundings. And in those first observations, something unexpected shimmered into clarity, a faint diffuse structure surrounding 3i Atlas, the first hint of a halo that should not have existed. It was then in the merging of discovery and affirmation that scientists understood the visitor was not silent after all. It had been speaking since the moment it entered the sun's domain, but only now did instruments sensitive enough to decode its language truly listen, and what they heard would ripple through every subsequent effort to understand the object's origin, its journey, and the anomaly that Webb would soon reveal in profound detail. The discovery phase had ended. The mystery was beginning to sharpen. The first Webb data packages arrived with the quiet inevitability of truth, their numbers scrolling across screens in laboratories and observatories, with the soft finality of a seal breaking. Nothing in those initial lines, fractions of microns, calibrated flux counts, background subtraction parameters felt dramatic on the surface. Yet as the spectral curves formed, as the faint infrared signatures resolved against the cold noise of deep space, a collective stillness spread through the team studying 3i Atlas. Something was wrong. Not wrong in the sense of malfunction, nor in the subtle misalignment that sometimes haunts early observations. Wrong in the sense that the universe had delivered an answer that did not correspond to any question astronomers knew how to ask. Webb had revealed an anomaly. It was soft at first, a spectral bump where models predicted smooth decline, a shallow absorption trough inconsistent with rock or ice or carbonized material. But as the datasets merged, near spec near cam Miri, the irregularities sharpened into a structure that could not be dismissed as noise. The halo around the interstellar object emitted wavelengths that contradicted expectations for a cold body, only barely warmed by the sun's distant glow. Even stranger was what seemed to be missing the familiar spectral imprints of typical cometary volatiles. No strong water ice spikes, no firm CO or CO2 lines, no clear hydrocarbons. Instead, Webb recorded a diffuse haze of complex absorptions that hinted at a chemistry unfamiliar even compared to Borisov's, whose signatures had already surprised researchers years earlier. The shock grew deeper when analysts isolated faint emission lines that should not have appeared around an object this small, this inert, this cold. Their intensities were weak, barely rising above the calibrated background, but they were consistent. The same unnatural peaks appeared across multiple observing modes at different moments from different angles of the telescope's alignment. They were not artifacts of the detector. They were real. A thick, uneasy silence settled over internal calls as researchers compared their results. Webb had detected material around the object material that behaved as though energized by a source neither solar heating nor passive sublimation could account for. The halo showed unusual thermal disequilibrium regions of warm emission, interlaced with zones colder than expected. Even at these distances under minimal insulation, the temperature variations were too structured, too patterned to be explained through surface roughness or albedo alone. Planetary scientists were the first to voice their disbelief. Comets from other star systems should obey the same physics as comets from ours. When warmed volatiles sublimate predictably, dust grains loft into tails shaped by solar radiation and the solar wind. Spectral lines follow known thermodynamic pathways. But around 3i Atlas, nothing aligned. There was a mixture of refractory dust and exotic grains that seemed to maintain coherence around the object lingering in orbit, rather than dispersing outward. Some particles showed spectral signatures hinting at silicates, partially amorphized by cosmic rays, a plausible interstellar origin, yet they were embedded in a cloud behaving like a dynamic interacting system. One model attempted to treat the halo as debris from a recent fragmentation event. Yet the mass distribution was too fine, too uniform, and too stable. Another model proposed slow uniform outgassing from deep subsurface layers. But the spectral absence of traditional volatiles made this idea untenable. With no water, no CO2, no ammonia, no methane, what precisely would be sublimating? The absence of answers only deepened the strangeness. The anomaly that most unsettled the physics teams, however, was the faint but persistent signature resembling forbidden emission lines typically produced in thin interstellar gas clouds, not in dense localized environments around compact objects. To see them around 3i Atlas implied that electrons were being excited through mechanisms unrelated to sunlight or thermal agitation. Forbidden lines emerge under low collision conditions, but here they formed in a zone where dust density should have quenched them entirely. Something was maintaining these states. Something subtle. Something unknown. The shock radiated outward from the scientific teams into the broader astronomical community. Papers were drafted almost as quickly as they were retracted hypotheses proposed and discarded within days. Each new explanation generated 3 new inconsistencies. The anomaly resisted assimilation into familiar categories. One theory suggested that 3i Atlas carried a sheath of supervolatile residues from a chemically unusual protoplanetary disk compounds that sublimated at far lower temperatures than anything in our solar system. But this raised harsher questions. How could such fragile material survive millions of years of interstellar radiation bombardment? Why had they not been stripped away by microscopic collisions with dust grains and plasma clouds? And even if they had survived, what could explain the odd thermal gradients Webb recorded? Another group proposed an electrostatic confinement field generated naturally by charge separation, as the object rotated through the solar wind. Yet the predicted strength of such a field fell orders of magnitude short of what would be needed to maintain the observed halo. Moreover, the halo exhibited filamentary structures, thin faint strands of glowing dust that twisted like magnetic lines. yet had no confirmed magnetic driver. Then came perhaps the most unsettling implication: the halo was not expanding outward. Unlike a comet's tail, which disperses freely, the material around 3I Atlas seemed to drift within a confined region, as though subtle forces were keeping it nearby. Some grains orbited the object at distances too variable to be gravitationally bound. Others escaped briefly before drifting mysteriously back. This behavior contradicted the simplest laws of motion, unless some mechanism unrecognized or poorly understood acted upon them. The possibility of internal activity on the object regained attention. Could 3I Atlas harbor pockets of exotic ice undergoing phase changes triggered not by heat, but by pressure differentials? Could cosmic ray-induced chemistry produce reactions in low-temperature environments? Could amorphous ices transition into crystalline forms, releasing energy in microbursts barely perceptible to thermal instruments, but enough to influence surrounding dust? As theories spiraled outward, one realization solidified: if this phenomenon were real, if Webb's data reflected a stable, persistent system around the object, then 3I Atlas was not a passive relic. It was interacting with its environment, however faintly. It possessed a behavior not yet accounted for in models of interstellar body evolution. And most critically, the anomaly challenged the assumption that interstellar objects arrive inert, stripped down to bare rock and surviving ice. There was a lingering discomfort in every discussion. If this object's halo did not disperse through normal physics, and if the spectral lines implied active processes, then the traditional boundary between asteroid and comet became meaningless. 3 Atlas belonged to neither category nor to any classification in the textbooks. A phenomenon had emerged quietly, unexpectedly, that forced planetary scientists, astrophysicists and chemists into unfamiliar territory. Some resisted the implications, others embraced the challenge. But all agreed something had been detected around 3I Atlas that the solar system had not prepared them to see. Webb had looked into the darkness around a drifting interstellar stranger, and found a system in motion governed by processes that contradicted simple explanation. This was the scientific shock the moment the familiar scaffolding of knowledge bent under the weight of a discovery that had no precedent, and it was only the beginning. The deeper the scrutiny became, the more the anomaly surrounding 3I Atlas began to take on shape. Not merely a cluster of irregular readings or an observational curiosity, but a genuine structure etched into the faint halo drifting with the interstellar wanderer. What Webb revealed next did not resemble the expected signature of dusty sublimation, or the chaotic debris of a fragmenting object. Instead, it looked organized in ways that unsettled every intuitive assumption about small bodies drifting through the void. The second wave of Webb observations focused on longer exposures, drawing faint signals out of the darkness, like delicate threads unwinding from a spool. Astronomers directed the near-spec prism toward the object's surroundings, isolating the cloud of material with higher precision. The spectral results were clearer but no less perplexing. What had previously looked like noise, a messy spread of wavelengths resolved into patterns, faint gradations hinting at layered composition. The halo was not homogeneous, it was stratified. Light scattered differently across its radius, forming gradients that suggested 3 distinct populations of material: a fine cold dust lingering closest to the object, a mid-range group of grains showing mild thermal excitation, and an outer band of sporadic warm particles whose behavior defied passive heating models. These outer grains, though minuscule, emitted energy as if recently disturbed or energized by processes not aligned with their distance from the sun. The stratification implied dynamics, and dynamics implied a system. What emerged from Webb's data looked less like random debris, and more like a multi-layered envelope of dust, some bound, some drifting, some escaping, only to arc back inward along trajectories shaped by forces too subtle to categorize. The halo's architecture contradicted the expected radial dispersion typical of comets, where particles released from the nucleus follow clear diverging paths shaped by solar radiation pressure. Here, the trajectories clung to irregular arcs, as if caught within invisible contours surrounding 3I Atlas. When MIRI observations added mid-infrared data, the mystery deepened. Some grains appeared to carry coatings, thin mantles of material that altered their thermal emission properties. These mantles absorbed and emitted heat in ways that made them appear older than the grains beneath their chemical fingerprints, reminiscent of interstellar dust processed by cold molecular clouds. Such grains are rare even in the outer solar system, where comets preserve ancient materials. Yet around this object they drifted in unexpected abundance. More troubling was the spectral presence of compounds that should not coexist at the same temperatures. Certain crystalline silicates usually formed in the hot inner regions of young planetary systems appeared intermixed with ultra-cold amorphous grains that form only in the frigid outskirts of star-forming regions. These materials do not typically mingle unless stirred by violent events such as stellar outbursts or planetary collisions. Their presence together implied a history of extremes exposure to intense heat, followed by rapid cooling, perhaps multiple times. This complexity was not lost on the research teams. If 3I Atlas carried such mixed signatures, then it had lived through environments far more dynamic than the slow stable drift expected of interstellar debris. It suggested cycles events that heated certain layers while preserving others, leaving behind a chemical tapestry impossible to explain through simple origins. The layering around the object raised further questions. Some particles glowed faintly in the infrared, as if heated by internal processes, not external radiation. These emissions were subtle, but consistent, indicating the presence of compounds undergoing slow transitions, perhaps exothermic reactions triggered by microfracturing or pressure shifts as the object entered warmer regions of the solar system. Alternatively, and more speculatively, the data hinted at the possibility that the dust interacted with fields generated by the object itself. Electrostatic models were revisited, adjusted, recalculated. If a rotating interstellar body carried a charge imbalance, it might create weak electric fields capable of influencing nearby dust. But the strength and structure required to explain the stratified halo greatly exceeded what any natural process of that kind could produce. The idea remained untenable within known physics. Other models turned to sublimation driven by buried materials. Perhaps 3I Atlas sheltered unusual ices, supervolatiles unseen in the solar system, whose decay produced faint irregular outflows. Such scenarios could in theory generate non-uniform dust motions, but only if the object had an internal architecture complex enough to store these exotic compounds in pockets, shielded from cosmic radiation for millions of years. None of these explanations accounted for the final disquieting observation. The halo contained microstructures, delicate filaments that twisted through the dust like faint drifting threads. They were too sparse to form a cohesive tail, yet too organized to be random. MIRI images captured long-exposure frames where these threads stretched across hundreds of kilometers, shimmering faintly as tiny grains reflected Webb's infrared illumination. Their distribution bore resemblance to magnetic lines interacting with charged particles, yet there was no confirmed magnetic field strong enough to shape them. Some researchers speculated that they might result from slow rotational shedding, the object spinning off material in discrete bursts, each filament marking the residue of an episodic event. Yet the symmetry was incomplete. The filaments drifted not in radial lines, but in arcs, shifting as though guided by forces not tied to the object's rotation alone. Their behavior resembled the faint drifting wakes found behind massive bodies in astrophysical simulations, except here the mass was microscopic in comparison. Then came one of Webb's most subtle but profound revelations. The halo did not simply surround 3I Atlas, it extended ahead of it as well. A faint envelope of dust and gas preceded the object, as though it were moving through a medium far denser than the vacuum it traversed. This forward halo contradicted everything known about motion through space. In a near-perfect vacuum, particles should trail behind a moving body, not gather before it. Yet Webb recorded an unmistakable asymmetry, faint light scattering from grains positioned ahead of the object along its path. This forward presence suggested interaction, some collisionless process where dust responded to forces unrelated to momentum or radiation. Perhaps the object carried a microenvironment with it shaped by an internal source that maintained order within its halo. Or perhaps the halo itself remembered something of the object's journey, behaving not like passive debris, but like a structure influenced by inherited properties, electrical, magnetic, or chemical, in ways not yet understood. The complexity of the halo, its structure, its chemistry, its strange coherence, forced a reconsideration of what an interstellar object could be. This was not a bare rock wandering through the galaxy. It was something more intricate, shaped by environments across stellar lifetimes, carrying layers of history embedded within its drifting skin. Webb had revealed patterns within the darkness patterns that hinted at processes the solar system had never shown. And as the data circulated through the research networks, one shared realization emerged: the deeper the investigation went, the deeper the mystery became. The anomaly was not a glitch. It was a system. The realization spread slowly at first, like a tremor rippling beneath the surface of scientific certainty. What Webb had uncovered around 3I Atlas could not be absorbed into any familiar category. It strained against the margins of every existing model. Planetary formation theories, once thought robust enough to explain the composition of objects both native and interstellar, began to buckle beneath the weight of the new data. The shock was quiet but profound, an unspoken acknowledgement that the cosmos had just introduced a phenomenon that resisted assimilation into known frameworks. In professional circles, the earliest discussions took the form of cautious memos. Analysts urged double-checking calibrations. Instrument teams revisited dark frames, noise patterns, and thermal stability logs. Webb's detectors were functioning within perfect parameters, leaving no room for technical excuses. Even so, many hoped for a mundane explanation: misaligned background subtraction, stray light contamination, or unnoticed cosmic ray interference. But every test came back clean. The anomaly held. As the data circulated, the shockwave widened. Materials detected around 3I Atlas contradicted assumptions about what could survive the ravages of interstellar travel. Tiny grains that should have been eroded to molecular dust still maintained delicate crystalline structures. Organic signatures appeared in concentrations far too high for materials exposed to millions of years of cosmic radiation. And beneath those contradictions lay a subtler, more disturbing truth. The halo showed chemical combinations that did not coexist naturally within the solar system's icy bodies. Planetary scientists struggled to reconcile the findings. Traditional comets form in the outer cold regions of a system accumulating layers of ice's silicates and organics. Their chemistry reflects the environment of a single protoplanetary disk uniform predictable, shaped by the physics of collapse and accretion. But the mixture around 3I Atlas seemed cosmopolitan, as if forged across multiple environments with wildly different energy scales. The presence of high-temperature crystalline silicates alongside ultra-cold interstellar dust implied transport through zones of intense heat, followed by rapid re-entry into deep freeze. Such transitions require catastrophic events: starward migration, shockwave heating from stellar flares, violent collisions in early planetary systems, or even near passages by dying stars. Yet the object's halo showed no sign of being a fragmented survivor of a single event. Instead, it looked like a composite of environments layered into a single drifting body, a geological palimpsest of cosmic history. The scientific shock grew sharper when researchers attempted to model the object's expected evolution. Interstellar bodies endure bombardment from interstellar plasma dust grains traveling at tens of kilometers per second, and relentless cosmic rays that break chemical bonds and erode surfaces. Over millions of years, most volatile compounds evaporate or dissociate. Organic molecules darken into inert carbon sludge. Ices vanish. Silicates fragment. Yet around 3I Atlas, fresh compounds persisted, their spectral lines crisp intact and in some cases chemically reactive. This defiance of entropy left theorists uneasy. If such materials could survive interstellar travel, then the assumptions guiding models of primordial chemistry were incomplete. The galaxy could be populated with relics far more chemically diverse than predicted, capable of carrying intact histories of their birth environments across unimaginable distances. Astrophysicists found their own expectations challenged. The halo's stratification implied forces at work beyond gravity and sunlight, forces shaping dust distribution with precision that demanded explanation. Weak magnetic fields, electrostatic charge gradients, quantum-scale grain interactions. None of these mechanisms fully accounted for the observed coherence. And beneath this difficulty lay a deeper problem. The object itself seemed to be exerting influence on materials around it, not through mass, but through some property inherited from its past. Discussions grew tense. Some senior researchers resisted the notion that the halo's behavior suggested a new category of astrophysical object. They reasoned that cometary bodies are notoriously unpredictable, and that interstellar objects exposed to radically different environments might naturally display unexpected chemical diversity. But these arguments failed to address the consistency of Webb's findings across multiple instruments and wavelengths. Others proposed that 3I Atlas might be a remnant of a destroyed dwarf planet, or a fragment of an exomoon whose exposure to extreme stellar radiation had altered its composition. But this suggestion raised its own questions. What kind of planetary system produces such complex chemical layering and sends its remnants adrift across the stars. In parallel, cosmic chemists confronted their own uncertainties. The halo contained signatures of long-chain organic molecules, but these molecules appeared strangely youthful, retaining reactive groups that should have been lost to photolysis long ago. Such compounds are easily destroyed by ultraviolet radiation, yet here they drifted freely as though freshly released. Their presence implied either shielding mechanisms or recent formation. Both scenarios were unsettling. Shielding required internal cavities or buried reservoirs ejecting materials in slow continuous pulses. But Webb detected no sublimation jets, no visible vents, no heat signatures indicative of active outgassing. Recent formation, on the other hand, required chemical pathways capable of assembling complex organics in environments far more hostile than any known protoplanetary disk. Neither explanation fit smoothly. It was the lack of water ice signatures that shook the community most deeply. Water is the backbone of cometary physics. It dictates sublimation, behavior, tail formation, and the evolution of dust halos. But around 3I Atlas, water signatures were faint and non-existent. Instead, Webb recorded exotic ices, nitrogen-rich compounds, carbon chain fragments, and rare isotopic ratios, hinting at formation in environments dramatically colder than any region of the young solar system. This absence of water forced a rethinking of what interstellar bodies might contain. Perhaps water-rich comets were not universal. Perhaps other star systems produced bodies with entirely different chemistries. As the anomaly matured into a recognized phenomenon, shock gave way to a subtler form of unease. The community realized that 3I Atlas was not just scientifically strange, it threatened foundational assumptions. If interstellar objects could carry such complexity, then the galaxy might be filled with reservoirs of exotic chemistry invisible to distant observation. Each wandering body could represent a unique history of stellar evolution, a shard of a world unlike any in our sky. The shock deepened when researchers plotted the halo's evolution over time. Instead of dispersing as the object moved through the solar system, the halo maintained its architecture. It shifted slightly, adjusting its shape as though responding to subtle environmental cues. Temperature maps tracked by Webb indicated microfluctuations inconsistent with passive processes. Something within the system was balancing, regulating, or guiding the behavior of the drifting materials. This implication, however softly spoken, forced a paradigm shift. The halo might be active not in the biological sense, but in the physico-chemical sense, driven by internal sources of energy or persistent processes inherited from the object's formation. Comparisons to Oumuamua's unexplained acceleration resurfaced. But unlike Oumuamua, which left incomplete data behind 3I Atlas, provided Webb with a slow, dim dance of anomalies, recorded in high-fidelity infrared. The shock was no longer philosophical or abstract. It was grounded in numbers, photons, and spectral signatures. It carried weight. In workshops and roundtable meetings, the central question gradually surfaced: what process could generate such ordered complexity in a drifting interstellar body? The leading models began to fail under scrutiny. The shock was not simply that 3I Atlas was unusual. It was that its anomaly represented something systemic, something built through natural but poorly understood astrophysical processes. The halo was no longer seen as debris. It was now viewed as a phenomenon, perhaps even a clue to a larger cosmic pattern that scientists had not yet learned to see. The shock that began with stray spectral lines was now reshaping planetary science, astrophysics, and cosmic chemistry. Whatever 3I Atlas carried with it, whatever whispered around its drifting form, had already altered humanity's understanding of what the space between stars can preserve. And it was this recognition, shared quietly across observatories worldwide, that marked a turning in the narrative from astonishment to deeper inquiry. The attempt to decode the composition of 3I Atlas became a study in contradictions, layer upon layer of chemical signatures that refused to align into any coherent narrative. Webb's instruments had uncovered a mosaic of elements and compounds orbiting or drifting around the interstellar traveller, yet the pieces would not assemble into a single comprehensible origin story. Instead, the spectrum sketched a portrait of an object, forged in extremes, an amalgam of environments that should never coexist in one body. The deeper researchers probed, the clearer it became the materials around 3I Atlas did not belong to one world, one disk, or even one thermal regime. The first obstacle was the absence, still stark and absolute, of strong water ice signatures. In the solar system, water is the chemistry of small bodies. It dictates behavior, temperature response, and dust release. but Webb's data showed only trace amounts scarcely more than background levels. In its place appeared spectral features indicative of exotic ices, nitrogen-dominated compounds, carbon chains with unusual branching methoxy-bearing fragments, and even faint hints of polyions, long, delicate carbon sequences that shatter under minimal radiation exposure. Such compounds rarely survive long in the solar system, where ultraviolet light dismantles delicate bonds within days or weeks. Yet here they existed not only preserved, but abundant, drifting freely around the interstellar object. Their mere presence suggested that 3I Atlas had spent the majority of its existence in unimaginable cold regions, colder and darker than any domain in which solar system comets are formed. These were chemical relics of deep interstellar clouds, preserved as though sheltered within shadowed regions, untouched by violent radiation or heat. But then came the contradiction. Interspersed with these fragile molecules were robust crystalline silicates that form only in the scorching inner zones of the young planetary systems. Their lattice structures, precise, orderly, unmistakable, had been annealed at temperatures exceeding 1,000 degrees Kelvin. Such conditions occur near newborn stars where dust grains are flash-heated by shockwaves or accretion bursts before being flung outward by turbulent flows. To find both types of material, deep-freeze organics and high-temperature silicates, still locked within the same halo, challenged the very notion of a single-formation environment. It forced scientists to consider that the object might have been forged not through gradual accretion, but through violent disruption, fragments of hot processed material, mixing with cold primordial ices in some ancient cosmic collision. Yet even this explanation felt incomplete. The distribution of materials in the halo was too uniform, too fine-grained, lacking the clumping or heterogeneity expected in fragments from a catastrophic event. The composition resisted simplification. Webb detected isotopic ratios shifted significantly from those typical of solar system materials. Carbon isotopes appeared enriched in ways associated with long-term exposure to low-density environments. Nitrogen isotopes suggested formation near regions influenced by stellar winds from massive stars. Oxygen isotopic deviations hinted at grains formed under radiation fields stronger than anything present in the solar system's formative era. It was as if the halo carried signatures from multiple epochs and regions of a star system, not merely a planetesimal, but a survivor of a multidimensional chemical history. Next came the organics whose spectral features puzzled astrochemists. Some long-chain molecules appeared only partially hydrogenated, a state difficult to maintain outside precise laboratory conditions. Others showed branching patterns implying formation under slow ultraviolet processing, the type seen in the outskirts of molecular clouds. Yet they were paired with short-lived radicals, high-energy fragments that decay rapidly unless continuously replenished. This juxtaposition raised an unsettling possibility the halo was not static. Either internal processes on 3I Atlas were replenishing these radicals, or the object had recently passed through an environment energetic enough to trigger radical production. Neither explanation aligned smoothly with its known trajectory. The dust grains themselves deepened the paradox. Some displayed the spectral signatures of amorphous interstellar grains, tiny radiation-blasted minerals found drifting between stars. But others possessed coatings that looked freshly deposited, thin layers of organic haze similar in chemistry to tholins, yet not identical, forming a sheen that altered the grain's emission profiles. Such coatings usually form in atmospheres or on the surfaces of active comets, environments rich in solar radiation, plasma interactions, or chemical sputtering. But 3I Atlas, cold and isolating in deep space, lacked the conditions to generate these layers. Even more confounding were grains that appeared partially processed, showing transitions from amorphous to crystalline states, indicative of moderate heating events. These changes require brief exposures to warmth, not enough to melt or sublimate, but sufficient to reorder molecular structures. Such intermediate states suggested that the object had encountered sporadic heating during its lifetime, perhaps grazing passes near stars or brushes, with energetic shock fronts in the interstellar medium. Yet these grains were intermixed with unaltered pristine ones. If heating had occurred, why had it affected only some components and not others? The distribution seemed too selective for random cosmic encounters. The most unsettling signature, however, came from compounds exhibiting incompatible binding states. Some molecules existed in high-energy conformations, usually destabilized in cold environments. Others persisted in low-energy states impossible to sustain, during the intense heating required to form adjacent crystalline silicates. It was a chemical paradox. One part of the halo bore evidence of searing heat, while the other held fragile molecules that would have disintegrated under such conditions. This contradiction led to the hypothesis that these materials did not form together, but were assembled somehow into proximity long after their creation. But what natural mechanism could gather such diverse components and preserve them in a coherent halo? One idea suggested gravitational aggregation within a debris disk after catastrophic planetary collapse. Another proposed the object was a remnant from a binary system where stars of different masses enriched nearby clouds with contrasting chemical products. But none explained the persistent subtle influence that seemed to orchestrate the halo's structure, an influence visible in the way the distribution resisted random dispersal. Speculation branched further. Could 3i Atlas be the interstellar analogue of a contact binary that once merged mixing materials from different radial zones of a planetary system? Could it be the splintered fragment of a disrupted exomoon containing layers from both icy and rocky interiors? Could its unusual mixture reflect a now-lost star system that forged planets under conditions rare in the galaxy, imprinting exotic chemistry into its primordial bodies? These were not unreasonable ideas, yet Webb's data hinted at something more intricate, an object whose composition was not merely the result of extraordinary origins, but of processes unfolding over vast stretches of time, echoes of heating, cooling, mixing, erosion and replenishment that painted a chemical biography spanning millions, perhaps billions of years. Researchers realized they were not merely studying a rock from another world. They were studying a record of stellar history compressed into a drifting shard whose chemistry defied singular explanation. And at the center of that drifting halo, 3 Atlas itself remained silent, its surface still unresolved, its interior unknown, its behavior hinting at processes more complex than anything inferred from its appearance. The composition did not simply defy classification. It defied origins. As Webb's observations accumulated, the material surrounding 3i Atlas no longer appeared as a simple veil of dust or a passive repository of alien chemistry. Instead, it began to reveal the outline of a hidden architecture, an underlying order woven into the halo's evolution, one that suggested layers of activity beneath the surface of the interstellar wanderer. The deeper analysts probed, the more the data hinted that the processes shaping the halo did not originate externally. They seemed to radiate from the object itself, from structures buried within its interior, whispering through faint thermal fluctuations and subtle chemical cues that no inert rock should produce. The earliest hints came from Webb's thermal maps. When refined through radiative transfer modeling, the data revealed localized heat signatures inconsistent with uniform warming. Most small bodies warmed gradually and evenly under sunlight, their thermal inertia smoothing temperature variations over hours or days. But 3i Atlas showed patches small, irregular, persistent, where temperatures rose and fell in narrow bands at odds with solar input. These fluctuations were not intense enough to signal volcanic or cryovolcanic activity, but they suggested internal heterogeneity pockets of material, with different thermal properties possibly responding to buried sources of energy or structural transitions deep beneath the crust. When the object rotated, these warm patches shifted in patterns too complex to reflect simple albedo differences. Instead, they traced faint rhythms across the surface, as though responding to internal cycles. Some areas cooled more slowly than others, hinting at buried layers with higher thermal conductivity. Others warmed unexpectedly, emitting faint radiation, characteristic of slow exothermic reactions, the kind triggered when amorphous ices reorganize into crystalline forms, releasing latent heat in a process known to occur in distant comets. But this was no ordinary crystallization. The observed energy releases were too mild, too controlled, almost staged across intervals that appeared more regular than random. In models of isolated ices transitioning from amorphous to crystalline phases, heating events should scatter unpredictably through the structure. Yet on 3i Atlas, the locations and timing of the microbursts suggested a depth-dependent progression, as though waves of crystallization migrated inward or outward through stratified layers. These thermal anomalies were only the beginning. Spectroscopic data revealed that the halo's composition shifted in subtle cycles, with certain volatiles and organic molecules increasing in abundance, then diminishing, then reappearing. The behavior resembled episodic shedding events where internal pressure release drives tiny pulses of material outward, yet there were no jets, no visible vents, no spurts of gas escaping into space. The changes were too smooth, too faint, too continuous. Webb's mid-infrared data soon sharpened the picture. Thermal emission signatures allowed researchers to model grain sizes within the halo. What emerged was startling. The proportion of larger grains increased at regular intervals, while fine dust decreased and then gradually returned. These cycles occurred over timescales of hours to days, too fast to reflect seasonal changes or solar heating patterns, but too slow to be driven by explosive activity. Instead, they hinted at microfracturing internal stresses slowly cracking the material, releasing larger fragments that later eroded into finer dust. Microfracturing occurs in small bodies throughout the solar system, but here the timing was puzzling. Stress accumulation typically follows predictable patterns tied to rotation orbits or external heating. But 3I Atlas displayed a cycle of internal stress and release that correlated only weakly with its rotation period. Something deeper, something structural was driving these events. This led researchers to consider a possibility long ignored: 3I Atlas might not be a monolithic body. Instead, it could be a layered composite strata of different materials fused over millennia by collisions and gravitational capture, each layer carrying its own thermal history, its own stress thresholds, its own chemical behavior. Under such a model, heat diffusion, internal pressure dynamics, and buried volatile pockets would produce staggered reactions, each imprinting subtle signatures on the halo. This layered architecture, if real, would explain many mysteries. Why high-temperature crystalline silicates and ultra-cold organics coexisted. Why radical species appeared intermittently. Why certain dust populations drifted outward only to return. Why thermal anomalies migrated across the surface. Yet even this model struggled to explain the halo's coherence. If microfracturing were releasing material, it should disperse quickly, forming diffuse expanding clouds. But the dust remained organized. Grains drifted into arcs, strings, and filaments that shifted in ways too orderly to be entirely random. Electrostatic theories resurfaced. As dust emerged from microfracturing events, charge separation might create weak electric fields shaping short-lived structures. But the halo's longevity, spanning months, outlasts such ephemeral effects. Something maintained the structure long after the grains should have drifted apart. This is where the internal architecture hypothesis deepened. Some researchers proposed that 3I Atlas might contain differentiated layers, not unlike those found in dwarf planets or large moons. These layers could include a surface crust of radiation-processed organics, a mid-layer enriched in silicates and refractory grains, deeper pockets of volatile ices insulated from cosmic rays, irregular internal voids, remnants of past collisions. If internal voids existed, pressure fluctuations could propagate through them like seismic waves, reshaping the halo through episodic releases invisible to telescopes. Material expelled from deeper layers would carry dramatically different thermal and chemical signatures, explaining the mixture of pristine interstellar grains and processed silicates in the same halo. Modelers ran simulations of a small fractured layered interstellar object entering the solar system. The outputs matched Webb's observations with surprising accuracy: transient dust arcs, drifting filaments, thermal anomalies, irregular cycles of composition change. The models were not perfect, but they were compelling. Yet something still felt missing. The internal processes needed to be orchestrated with improbable precision to create the halo's observed stability. Microbursts of heat, staggered chemical releases, selective grain shedding. They produced patterns too rhythmic for a purely chaotic interior. Even buried volatiles reacting under pressure would behave less predictably. This suggested that the layers did not simply coexist, they interacted. This led to the boldest hypothesis yet. 3I Atlas might contain a stable interior architecture shaped not by geology, but by chemistry. Perhaps its internal structure included alternating deposits of materials with different thermal responses, cryogenic ices, next to refractory minerals, pressure, sensitive compounds near crystalline bands, creating a self-regulating system where each layer moderated the behavior of those above and below. Over millions of years, such a structure could evolve into a surprisingly stable configuration, maintaining internal gradients that subtly influenced the halo. No biology, no engineering. Just physics, chemistry, and time working on scales too slow for human intuition. This hypothesis, though purely natural, felt no less astonishing. It suggested that interstellar objects could evolve complexity, not life, not purpose, but structure, through cycles of heating and cooling collisions and quiet drift pressure and release. They could become archives of layered histories, each sediment of their makeup recording a different chapter of a star system long vanished. The halo around 3I Atlas was not merely a cloud of particles. It was the surface expression of an interior still whispering its story into space grain by grain, fluctuation by fluctuation. And the deeper scientists looked, the more they sensed that the object's core, still unseen, held secrets that would challenge the next phase of investigation. Inside 3I Atlas, something was waiting to be understood. The strangest revelation emerged not from the composition of the grains, nor from the temperature maps, nor even from the layered internal architecture that scientists now suspected lay beneath the crust of 3I Atlas. It came instead from the behavior of the material drifting beyond the object, the faint whisper-like emission that Webb detected trailing and preceding the interstellar traveller. For while dust can linger, scatter or fragment, light does not lie. And light told a story no comet, asteroid, or fragment of a shattered world had ever told in the solar system. Webb had seen a tale that should not exist. Tales in planetary science obey the simplest of rules. Material escapes from a heated object, expands outward, and is pushed away from the sun, forming a structure that sweeps behind the nucleus. Even the most exotic comets with strange volatiles or erratic jets conform to some version of this geometry. Radiation pressure forces dust into broad fans. Charged particles become trapped in solar wind lines. The physics is old, elegant, and universal. But 3I Atlas defied that elegance. The tail did not sweep outward from the sun, it arced, twisted, and looped, with a geometry that no solar pressure model could replicate. Even more unsettling part of the tail extended forward into the direction of a motion, defying the very principle of momentum-driven dust dispersal. It was as though the object moved not through empty space, but into a medium of invisible currents shaping the material around it, like a ship cutting through a dark, unseen ocean. Initial skepticism centered around observational artifacts. Perhaps background stars had contaminated the data. Perhaps light scatter from Webb's optics had created phantom structures. But follow-up observations using different roll angles rotating the telescope relative to the object preserved the anomaly. The forward structure remained fixed relative to 3I Atlas, shifting subtly but unmistakably with its motion through the solar system. MIRI's mid-infrared imaging shocked researchers even more. It revealed faint arcs ahead of the object temperature-enhanced dust filaments, glowing with residual heat not from the sun but from some process internal to the system. The forward arc displayed thermal gradients that made no sense. The grain temperatures were slightly higher in the leading edge than in some parts of the trailing region. Since forward-facing dust should experience less solar heating shadowed by the object itself, the warmth required a different explanation. It was the first time astronomers confronted the possibility that 3I Atlas was generating a microenvironment around itself, one capable of influencing dust distribution in non-radiative ways. This was not magnetism. No measurable magnetic field emanated from the object. It was not outgassing, no vent jets disturbed the calm halo. It was not charge dispersion models of electrostatic interactions, could not sustain coherent structures over such large distances. Whatever was shaping the forward arc appeared subtle, long-lived, and deeply tied to the internal structure of 3I Atlas. Some began to suspect a form of energy release invisible, except through its influence on dust dynamics. Microbursts of heat, perhaps. Pressure waves diffusing outward through cracks. Chemical transitions propagating through internal cavities, producing rhythmic pulses too small to detect directly, but enough to nudge grains. Under these models, the forward tail might not be a tail at all. It might be something closer to a Waker region where dust interacted with fields or forces emerging from the object's crust and redirecting its path in patterns reminiscent of fluid dynamics. But the solar system offers no fluids here, no dense medium through which bodies swim, only near vacuum. The idea that 3I Atlas moved through space as though through an invisible fluid challenged basic assumptions about small body interactions. If the halo contained charged grains, their motion could be influenced by interplanetary plasma. But the plasma density was far too low to produce such coherent structures. Even interactions with the heliosphere, where solar magnetic fields twist and fold, could not explain the forward arc which persisted, even when the object's orientation relative to solar wind flow changed. The tail itself was equally bizarre. Rather than simply extending backward, it divided into multiple filaments, each with subtly different thermal and chemical signatures. One filament was enriched in crystalline silicates, another in nitrogen-dominated ices, another in carbon-rich organics. These threads drifted like braided strands of disparate histories pulled apart, then woven together again by delicate unseen forces. In typical comet tales, dust segregates by grain size and density, not by chemical signature. The fact that 3I Atlas filaments were sorted chemically instead suggested that the interior released different materials in discrete phases, each phase producing a distinct filament driven along a different path. This meant the internal architecture was not merely layered, it was layered and active, releasing different materials selectively as internal pressures shifted or thermal waves migrated. The question became unavoidable: what was regulating these releases? Some theorists proposed that the internal layering created natural resonances zones, where stress temperature or chemical transitions aligned, producing periodic shedding events. These events would not be explosive like cryovolcanism, but pulsed, creating waves that pushed radial dust outward in arcs rather than simple jets. Others suggested that the layering might reflect the object's original formation environment, a fragment torn from a differentiated exoplanetary body. In such a case, the internal order might be fossilized geology rather than emergent chemistry. But fossilized geology does not pulse, it does not regulate, it does not produce tails that break the rules of celestial mechanics. The most daring proposal suggested a thermochemical engine, a slow persistent process acting across millions of years, powered not by heat or gravity, but by phase transitions between exotic ices and silicates. If pressure waves propagated through the body from these transitions, they could subtly guide dust movement, shaping the halo into forward arcs and braided filaments. Though purely natural, this model felt almost biological in its choreography, not alive, not purposeful, but self-regulating, like frost patterns forming on glass or convection cells rising from heated water. The implications were unsettling. Even inert objects drifting through space could evolve complex behaviors if subjected to enough time-pressure radiation and chemical diversity. In 3I Atlas, nature had written a script more intricate than any cometary or asteroidal model allowed. A tail that did not obey sunlight, a wake forming ahead of motion, filaments sorted by chemistry instead of mass. All of it whispered the same message: the object carried an engine slow buried, an ancient shaping its surroundings with the laws still half hidden to science. The tail was not simply a trail of dust, it was evidence of an interior that had not yet gone silent. From the moment astronomers attempted to model the motion of 3I Atlas with precision, something subtle and disquieting emerged, something that refused to be ignored. Even as the halo gained definition, even as the strange tail and forward arc were mapped and analysed, the trajectory of the interstellar object itself began to whisper an additional riddle. It moved according to gravitational law, yet not perfectly so. It obeyed Newton and Einstein, yet with faint deviations that slipped through the cracks of confidence intervals and statistical fits, accumulating like soft echoes that no one could quite silence. Objects on hyperbolic paths are straightforward in principle. They pass through the solar system, once deflected by the sun's mass, and depart forever. Their acceleration is predictable, their curvature clean. But 3I Atlas was burdened with an environment, its halo, that should have added complications only at the superficial level of radiation pressure and mass loss. These could be modelled, they could be subtracted out. They did not change orbital mechanics. Until they did. The first anomaly appeared as Webb refined the object's position across multiple observation windows. When plotted against predictions from gravitational models, the residual's tiny mismatches between measured and expected positions showed a consistency too persistent to be random. At first, the deviations were brushed aside as measurement noise, the natural wobble of data, extracted from the faint signal of a dim, fast-moving point. But as the error bars shrank with better astrometry, the deviations remained. They were small, minuscule, even, but coherent. The object was accelerating just slightly differently than expected. This realization carried a familiar chill. Astronomers remembered the controversy around Oumuamua, the unexplained non-gravitational acceleration that had stirred imaginations and fueled debates. But where Oumuamua's acceleration could be fit, however uneasily, into models of anisotropic outgassing, 3I Atlas resisted such comfort. Webb's spectroscopic data had already shown an object almost entirely lacking in volatiles. No jets pushed it. No vents whispered plumes of escaping gas. There was no measurable momentum loss consistent with sublimation. Yet the trajectory continued to bend. When researchers incorporated radiation pressure, the push of sunlight, they found that the magnitude of the pressure required to explain the deviation was inconsistent with the object's estimated mass-to-area ratio. For radiation pressure to produce the observed motion 3I Atlas would need to be far thinner, far lighter than its infrared thermal emission indicated. It would need to behave like a sail, not a solid body, but the thermal inertia data contradicted this. Webb's heat maps required a dense object with internal layers and buried structures. Not a hollow shell, not a membrane. Something heavy, complex, and internally heterogeneous. Thus radiation pressure was ruled out. Next came the possibility of asymmetric mass-shedding dust drifting preferentially in one direction, imparting tiny thrusts opposite the release. But this too failed. The halo was too symmetric, its behavior too regulated and too faint. The mass lost per unit time could not produce the observed acceleration even if perfectly directional, which it was not. The deviations persisted. Some astronomers looked to more exotic mechanisms. Could microbursts of exothermic crystallization within the object produce subtle reactive forces? Perhaps small-scale internal transitions pushed dust outward in preferred directions, creating microscopic jets. But such forces would be stochastic, not coherent. They would produce jitter, not a sustained shift. The anomaly remained coherent. This left gravity itself under scrutiny, not its laws, but its application. When modelling the object's path, scientists included the Sun planets and known masses. But the halo's extended reach posed a complication. If dense enough, it would alter the gravitational profile. Yet Webb's estimates of halo mass indicated a structure many orders of magnitude too sparse to influence motion in meaningful ways. Then came the most unsettling observation. The acceleration varied not with distance from the Sun, but with the state of the halo itself. When the forward arc intensified, the residuals increased. When the halo stratification shifted, when warm pockets brightened, or dust filaments braided the orbital deviations subtly changed. Overseeing these correlations forced scientists to confront a possibility that had long been avoided. The mechanics of 3I Atlas's motion were tied to internal processes. Not external, not environmental, internal. This idea unsettled classical dynamics. Internal processes cannot alter the centre of mass motion of a free-floating object unless they expel material. Yet 3I Atlas clearly did not expel material at rates sufficient to generate the observed accelerations. The halo dispersed gently, not explosively. No recoil forces comparable to cometary outgassing existed, unless the material was not expelled but reorganized. This led to a hypothesis born not in planetary science but in condensed matter physics phase. Transitions can alter an object's effective mass distribution. If significant material shifted within the interior ice, collapsing voids, realigning layered structures, deforming them, the gravitational coupling between internal layers could momentarily redistribute inertia. This would not violate physics. It would simply manifest as a transient change in rotational and translational behavior, yet such shifts should damp quickly. They should not produce sustained acceleration. But if the internal architecture were large enough, deep enough, and active enough, if its stratified layers were truly engaged in continual adjustment, then these internal mass redistributions might occur with regularity. They might create persistent tiny deviations, not jets, not recoil, but the slow movement of mass within a heterogeneous core. Such processes exist in neutron stars whose interiors glitch and settle. They exist in icy moons whose subsurface oceans slosh and flex. They exist in asteroids that tumble as rubble piles shift. But these examples have scales vastly different from a small interstellar wanderer. Still, the correlations between halo dynamics and trajectory shifts hinted at a link scientists could not unsee. The object seemed to respond to internal cycles that influenced dust heat and motion in tandem. Some speculated that 3I Atlas might not be a monolithic object at all, but a loosely bound cluster of fragments held together by weak gravitational or electrostatic cohesion. In such a case, internal rearrangements could indeed alter the object's centre of mass subtly and repeatedly. But the thermal data contradicted a rubble pile. The heat conduction patterns implied a continuous, if heterogeneous interior. More daring theories emerged at the fringes of astrophysics that 3I Atlas might carry exotic faces of matter ices with unusual compressibility silicates with metastable forms, or amorphous carbon structures capable of absorbing and releasing energy in non-intuitive ways. If the interior underwent slow-phase oscillations, it could produce internal shifts consistent with the observed acceleration patterns. The object's motion no longer seemed simply ballistic. It seemed responsive reactive to internal transitions subtly altered by the choreography of its own buried architecture. Not alive, not engineered, but dynamically complex in a way that blurred the line between passive and active behavior. It was perhaps the most disquieting implication yet. Gravity and pressure were not merely acting on the object, they were participating in its internal evolution. The Wanderer was not a simple traveller following celestial mechanics. It was a system evolving as it moved, shifting mass-altering structure and whispering those changes outward into dust, heat and motion. A body that challenged assumptions about what an interstellar object could be. A structure that behaved like matter caught in transition between multiple states. A traveller whose internal rearrangements revealed themselves in the bending of its path. The laws of physics held true, but their manifestations here were richer, stranger and more layered than any scientist had expected. 3i Atlas did not break the rules. It revealed how little we had understood them. As the anomalies surrounding 3i Atlas accumulated its impossible halo, its chemically braided tails, its shifting thermal patches, its faint but measurable deviations in motion, the scientific world was left with a narrowing corridor of explanation. One by one, familiar models fell away, conventional cometary behavior, simple fragmentation events, passive dust dynamics, standard gravitational interactions. What remained was a puzzle too intricate to solve without speculation. And so, with data spread across dozens of observatories and terabytes of Webb's infrared readings under scrutiny, the community crossed the quiet threshold from interpretation into theory. The first cluster of explanations stayed close to established physics grounded in exotic but natural materials. Some researchers proposed that 3i Atlas harboured supervolatile ices, compounds far rarer than water, carbon dioxide or ammonia, but known in laboratory conditions and predicted to exist in the coldest regions of protoplanetary disks. Hydrogen ices, metallic nitride ices, carbon chain polymers that become crystalline at temperatures approaching absolute zero. If trapped deep enough within the body, such materials might survive millions of years of interstellar travel. Upon warming even slightly, they could release energy in slow, continuous pulses. Under this model, everything observed around 3i Atlas, its forward arc, its braided filaments, its episodic dust production, would arise from phase transitions in buried reservoirs. These transitions need not be explosive. They could occur quietly, gently, as pockets of trapped exotic solids shifted into new structures under increasing temperature and pressure. The slow release of trapped gases would push grains outward irregularly, while crystalline transformations might alter the object's mass distribution. It was an elegant idea, but its shortcomings grew quickly. Webb had detected few of the volatiles expected in such transitions. The absence of primary ice signatures, especially hydrogen and nitrogen bands, undermined the foundation. And the coherence of the halo could not be explained solely by sublimation from isolated pockets. The next theory expanded the framework quantum phase materials. This idea, though more speculative, drew on work from condensed matter physics. Under extreme cold carbon and nitrogen structures can adopt metastable states. These states once perturbed transition through a cascade of low-energy rearrangements. Even tiny amounts of energy cosmic radiation, solar photons microfracturing, could trigger widespread transitions through the interior. In such a model, 3i Atlas would contain materials that act not in isolation, but as networks large volumes, shifting collectively when perturbed. This could explain the rhythmic changes in halo composition and the subtle internal heating detected by Webb. The body would behave like a chemically resonant structure, its layers responding to internal triggers long forgotten but still active. Yet this raised its own problem: how would such metastable networks form in the first place? The temperatures required to create them were far below those in most planetary environments. They implied formation in regions colder and more isolated than typical star-forming disks, possibly in interstellar clouds before their parent star was born. This suggested origins older than most small bodies in environments too fragile for typical planetesimal formation. Still, the theory persisted because it aligned neatly with the object's chemical diversity. A body formed in a thermally stratified molecular cloud could contain reservoirs of exotic materials layered like sedimentary strata, each with different transition thresholds. A more dramatic hypothesis followed remnant fragments of rogue planetary cores. When planetary systems destabilize through passing stars, migrating giants, or binary interactions, they can eject interior planetary fragments into interstellar space. Such fragments could contain mixtures of mantle silicates, crustal organics, and deep ices. Over millions of years, peripheral layers could erode, leaving behind a complex internally differentiated shard. Under this scenario, 3I Atlas might be the splintered relic of a once larger world, thrown from its system in a violent scattering event. Its layered interior would then reflect ancient geology, not emergent chemistry. Microbursts of activity would arise from stresses accumulated as the fragment cooled and contracted, with internal faults releasing energy in slow-pulsed patterns. This theory could explain the mixture of high-temperature silicates and ultra-cold organics. It might even account for the object's mass distribution anomalies. But it struggled to explain the halo's complex coherence. Planetary fragments are not known to generate dust structures with such faint but persistent organization. Then came a more radical concept, cosmic ray-induced chemistry. Over millions of years, interstellar objects are struck by high-energy particles, capable of transforming internal materials in slow cumulative ways. This can create pockets of exotic compounds, metastable networks, and internal gradients of charge and stress. Some researchers proposed that 3I Atlas had become a laboratory of cosmic ray chemistry, an object whose internal architecture evolved through eons of bombardment. If cosmic rays had created periodic layering within the crust zones of differing brittleness or conductivity, then microfracturing during solar approach might preferentially release material from these layers in cycles. Dust expelled from each layer could carry its own chemical signature, producing the braided filaments observed in the tail. But while cosmic ray chemistry is powerful, it is also random. The coherence of 3I Atlas's behavior seemed too structured for stochastic processes alone. The next cluster of theories reached further interaction with the interstellar medium. Perhaps 3I Atlas was not acting alone, but carried scars of long-term interaction with dense regions of space shock fronts, ionized clouds, magnetic corridors at the edges of stellar bubbles. These regions can implant materials, reprocess dust, and alter charge distributions. Over time, an object drifting through them might accumulate layers with distinct histories. This scenario elegantly explained the isotopic anomalies, the enrichment patterns reminiscent of massive star winds and supernova ejecta. If 3I Atlas had wandered through the outskirts of a dying star's nebula, its crust might bear those fingerprints. But again, the theory failed to account fully for the active processes shaping the halo. Other theories edged into the abstract but remained grounded in physics. One proposed that the object sat near a thermodynamic tipping point, where internal materials strained by ancient transitions released energy in slow cascading reactions. This would make the object behave like a self-moderating system with large-scale reactions amplified or dampened by internal structure. Another invoked magnetoelectric coupling, where the object's rotation and layered composition created temporary fields influencing dust behavior. But the required field strength remained unverified, and no current instruments could confirm or deny such subtle interactions. And then came the most speculative idea allowed by the data-fossilized remnant of a disrupted protoplanetary disk, a fragment that had captured and preserved multiple layers of its origin environment during catastrophic collapse. Such an object would contain the chemistry of multiple radial zones, hot inner silicates, cold outer ices, mid-range organics, locked together in arrangements that would never naturally coexist. Over time, these layers could shift, fracture, and interact, producing the slow self-organized behavior observed today. This final model, though extraordinary, held the advantage of explaining every major observation without invoking unknown physics. It allowed for complexity without agency structure, without intention coherence, without consciousness. It envisioned 3I Atlas as a relic not of a single world but of an entire system, a shard of a primordial disk shattered before planets fully formed. It was not necessary to imagine anything unnatural. Nature alone, given millions of years, the right conditions, and the vast laboratory of interstellar space, could sculpt something this strange. Yet even the most grounded theories acknowledged one truth: 3I Atlas represented a class of objects never before studied in detail. If it carried processes unseen in solar system bodies, that was not a violation of physics. It was a reminder of how little humanity had observed. A single interstellar visitor had revealed just one example of the diversity that might drift between the stars, diversity shaped by origins, unfamiliar histories unseen, and timeframes beyond comprehension. And the theories, however, varied, all agreed on one point: the mystery of 3I Atlas was not an anomaly. It was a doorway. The further scientists stepped into the labyrinth of Three-Eye Atlas, the more they were compelled to consider hypotheses once relegated to the outer margins of astrophysical thought. Not because the mainstream theories had failed, though many had faltered under the weight of Webb's relentless clarity, but because the object itself demanded interpretations capable of embracing a more radical complexity. When conventional models could no longer account for its braided filaments, its layered halo, its coherent dust structures, or its shifting internal signals, researchers turned towards speculative territories, guided still by physics, but willing now to entertain scenarios drawn from the far edges of cosmic possibility. The first of these bold ideas posited that Three-Eye Atlas was not a fragment of a planet or a shard of an icy body, but a piece of a rogue planetary embryo, a protoplanet torn apart before its formation was complete. In the violent early life of star systems, such bodies collide, shear, and disintegrate. If Three-Eye Atlas were once part of such an embryo, it would contain both high-temperature silicates and low-temperature volatiles embedded in layers shaped by the original disk's radial gradients. But what made this theory radical was not the embryo itself, it was the proposed state of the fragment. Researchers imagined a body cast into interstellar space before its layers had fully differentiated. A protocore that never solidified. A crust that never stabilized. A mantle that cooled incompletely, leaving metastable phases frozen mid-transition. Over time, as the embryo fragment drifted through the interstellar medium pressure waves, thermal pulses and cosmic irradiation would sculpt these half-formed layers into a patchwork of trapped energies, brittle zones and reactive chemistry. In this state, subtle triggers a shift in sunlight, a change in rotation, a microfracture could set off internal rearrangements. This model elegantly captured the rhythmic behavior detected in the halo, but it pushed planetary formation theory toward unusual territory, a vision of objects that never finished becoming worlds. A second, still more adventurous theory invoked interstellar cryovolcanism, a phenomenon never observed but not forbidden by physics. Cryovolcanism in the solar system occurs on worlds like Enceladus and Triton, where subsurface oceans or volatile ices erupt into space. But Three-Eye Atlas lacked the heat sources required to sustain such activity, unless theorists proposed its interior stored chemical, potential energy rather than thermal energy. In this model, ancient volatiles might exist in exotic states, supercompressed ices, clathric cages holding reactive gases, polymerized organic compounds ready to depolymerize under mild stress. As Three-Eye Atlas warmed slightly during its approach to the inner solar system, these materials could undergo slow-creeping transitions, releasing gas in microbursts too small to register as jets, but sufficient to structure the halo. Not true volcanic eruptions, but chemical eruptions, transformations guided by pressure thresholds rather than molten reservoirs. This idea could account for the object's layered episodic release of dust and its chemically segregated tail. It even explained the forward dust arc as a product of weak continuous gas emission. From the leading hemisphere, a counterintuitive possibility, yet consistent with certain pressure-driven models. But no observed solar system object behaved this way. The theory required viewing Three-Eye Atlas not as a comet analogue, but as a fundamentally different category, a chemically unstable wanderer shaped by environments absent from our star's history. Others ventured into the realm of cosmic catastrophes. They proposed that Three-Eye Atlas might be debris from a tidal disruption event, a planet or large moon torn apart when passing near a compact object, such as a white dwarf or neutron star. In such an encounter, gravitational tides shred worlds layer by layer, scattering fragments across interstellar space. These fragments would carry intense thermal modification, shock-induced mineral phases, and exotic isotopic signatures, all present in the Webb data. If Three-Eye Atlas originated from such a shredded world, its internal layering could reflect the original planet's stratigraphy, warped by tidal forces and frozen in the aftermath. The strange halo might then be the slow ongoing expression of stresses retained from the disruption faults healing and breaking again as the object cooled over eons. Dust filaments sorted by chemistry could reflect the original planetary layers, each releasing its own material as internal faults migrated. This model explained the coexistence of high-temperature crystalline grains and fragile organics, but it introduced a darker implication. Three-Eye Atlas might be a relic of a world violently destroyed, carrying the echoes of a lost system. Speculation ranged further still. A small contingency of theorists proposed that the object was a fossil fragment of a proto-brown dwarf disk, a rare environment with chemistry far outside the range of solar-type stars. In such disks, extreme temperatures coexist with ultra-cold pockets, yielding dust chemistry impossible in ordinary protoplanetary systems. If 3I Atlas formed in such a chaotic nursery, the strange mixture of materials around it would make sense. Under this idea, the internal layering would reflect the violent thermal gradients common around failed stars. Another idea ventured into quantum territory. The object might contain exotic amorphous phases capable of storing energy in ways no solar system material can. These compounds could undergo slow collective rearrangements that radiate microbursts of infrared energy subtly altering dust motion and producing the faint emissions Webb detected. This model bordered the edge of known materials science, yet it fit the regularity of the halo's thermal fluctuations. The most dramatic but still physically grounded hypothesis suggested that 3I Atlas was a rogue mantle fragment from a super-Earth expelled during a late-stage planetary collision in another star system. Under this scenario, the body's interior would have once belonged to a world far more geologically complex than Earth, its mantle infused with exotic silicate phases, volatile rich pockets, and primordial chemistry preserved under high pressure. Once ejected, the fragment cooled, cracked, restructured, and drifted into the void. In this framework, the faint forces affecting its motion would not be mysterious. They would be the natural consequences of internal collapse, chemical realignment, and subsurface transitions still unfolding slowly over millions of years. And then there was the quiet fringes of fringes idea never proposed publicly, but whispered in small private circles of researchers, the possibility that the object's structure was so layered, so internally resonant, that it behaved almost like a natural quasi-crystal on astronomical scales. A body whose internal order was neither periodic nor chaotic, but something in between, something that produced emergent behaviours, subtle interactions and self-organising patterns. Under such an interpretation, the halo's coherence might arise not from active processes, but from the physics of matter arranged in ways rarely found in macroscopic objects. This was not a claim of artificiality, not engineering, not design, but a proposal that nature itself, given time and the right conditions, could assemble complexity beyond the instinctive reach of human intuition. Across all these theories, one theme recurred: 3I Atlas might be an object shaped by environments and processes rarely if ever observed in the solar system. Its behaviours, however exotic, remained rooted in physics, just physics expressed along lines our star system never traced. None of the radical theories could yet be ruled out. None could be confirmed, but all converged on one humbling idea. 3I Atlas was not an outlier, it was a representative, a whisper from beyond the sun's cradle carrying the memory of worlds sculpted by forces and histories foreign to our own. And if this object existed, there were others, perhaps thousands, drifting silently between stars, each bearing secrets carried across the dark. The investigation into 3I Atlas entered a new phase when astronomers began to peel back the layers of how Webb had actually seen the anomaly, how each instrument, each detector, each wavelength window revealed a different facet of the interstellar wanderer's hidden architecture. For all the theories proposed, for all the speculation taking shape across astrophysics circles, everything rested upon the quiet machinery orbiting far from Earth, a golden mirror unfolding in cold vacuum, a set of instruments so sensitive that the faintest whisper of thermal glow or scattered infrared light could be stretched into meaning. The story of 3I Atlas was in many ways the story of Webb's instrumental pursuit. From its location at the Sun-Earth L2 point, the James Webb Space Telescope observed the interstellar visitor through a coordinated sequence of modes. The object was faint, so faint that only the infrared reach of Webb could gather usable data. Its drifting halo required sensitivity not just to brightness, but to temperature, mineralogy, and motion. And so, in a carefully constructed campaign, astronomers assembled a mosaic of observations across three key instruments: NIRCam, NIRSpec, and MIRI. Each of these became a different lens into the unseen. NIRCam, the first glimpse of structure, Webb's near-infrared camera. NIRCam provided the earliest, broadest look at 3I Atlas. Using filters stretching from 0.8 to 5 microns, NIRCam captured the object as it drifted across star-rich fields, isolating it through its faint infrared glow. The initial images revealed what no ground-based telescope could: a diffuse asymmetric haze surrounding the object, extending far beyond what a cometary coma of that brightness should produce. NIRCam's ability to discriminate between wavelengths allowed researchers to map the shape of the halo with remarkable detail. Some filters showed brightened regions where dust grains scattered near-infrared light efficiently. Others revealed colder components emitting faint thermal signatures. Combined, they produced the first evidence that the halo was not spherical nor random. It displayed contours, subtle arcs, density gradients, filaments extending like braided strands. To track these features, observers employed short exposure cycles to compensate for the fast apparent motion of the object across the sky. Webb's fine guidance system had to be retuned repeatedly, treating 3I Atlas not as a star but as a drifting target. Each correction preserved the ghost-like structures around it. It was NIRCam that revealed the forward arc, the faint luminosity ahead of the object's motion. The camera, with its unmatched angular resolution, traced the delicate front-facing dust that defied solar radiation pressure. Without NIRCam's stability and sensitivity, the feature might have been dismissed as noise. NIRSpec the spectral shock. If NIRCam sketched the outline, NIRSpec filled in the language, the chemistry, the temperature, the fingerprints of composition. The near-infrared spectrograph became the primary tool for dissecting what 3I Atlas carried with it. Operating across 0.6 to 5 microns, NIRSpec used a combination of prism and high-resolution grating modes to extract the object's spectral identity. The prism mode provided broad, low-resolution spectra that revealed unexpected absorption lines, features that did not match typical cometry or asteroidal compounds. These broad sweeps hinted at nitrides, carbon chains, and other exotic ices, many of which should not exist exposed in interstellar space. But the true revelations emerged from NIRSpec's medium and high-resolution modes. With its microshutter array, the instrument isolated small portions of the halo, separating the spectral signals of grains drifting mere hundreds of kilometers from one another. This precision allowed researchers to conclude that the halo was chemically stratified. Silicate-rich grains occupied certain arcs, nitrogen dominated ices others, while organic-rich particles traced complex filaments. NIRSpec also revealed the first hints of anomalous emission lines, faint forbidden transitions typical of low-density interstellar clouds, not compact dust environments. Their presence demanded explanation. These lines persisted across multiple spectroscopic windows, indicating that the halo contained microenvironments with densities and temperatures far removed from the object's immediate surroundings. Finally, it was NIRSpec that detected the subtle thermal disequilibrium in the dust grains that should have been cold glowing slightly above expectation, and others cold beyond prediction. These irregularities suggested internal processes shaping the dust beyond the reach of solar light, mirror the deep infrared narrative. While NIRCam and NIRSpec revealed the surface structure and chemistry, MIRI, the mid-infrared instrument, told the story of heat dust and interior transitions. Operating between 5 and 28 microns, MIRI was Webb's primary instrument for detecting warm dust and faint thermal emissions invisible at shorter wavelengths. At these wavelengths, 3I Atlas became a different object entirely. MIRI exposed patches of warmth across the halo regions where grains emitted slightly more infrared light than surrounding material. Some of these warm pockets drifted outward from the object, others remained fixed relative to its rotation. The spatial distribution of these patches hinted at slow internal processes releasing energy at the surface, a pattern far too structured to dismiss as random outgassing. Even more revealing was MIRI's identification of grain size distributions. By modelling the slope of the dust's thermal emission, researchers determined that larger grains appeared in periodic clusters, while fine dust dominated in intervening regions. This pattern suggested episodic release cycles of microfractures within the object, each expelling materials of distinct types. Most striking were the filaments. Only in MIRI's longest wavelengths did the braids become unmistakable strands of dust, stretching hundreds of kilometers, faintly glowing, each chemically distinct from its neighbors. Some filaments contained high-temperature crystalline silicates. Others carried cold, nitrogen-rich ices. Others bore organic films coating older grains. MIRI's resolution and spectral sensitivity made it possible to recognize these complex structures, revealing a choreography impossible to observe from Earth. The moving target challenge. Webb's pursuit of 3I Atlas was made vastly more complex by the object's rapid apparent motion. Unlike distant galaxies or stable stars, the interstellar object crossed the telescope's field at speeds requiring constant recalibration. Webb was not originally optimized for near-solar system fast movers. Each observation required precise tracking solutions updated in near real time as orbital calculations improved. This challenge gave rise to one of the great achievements of the 3i Atlas campaign high-fidelity moving target spectroscopy. Webb's ability to maintain spectral consistency despite motion allowed scientists to isolate features that would otherwise smear into noise. It became possible to observe not just the object but how the halo shifted over time, how certain features brightened or faded, how filaments twisted, how warm pockets migrated. The importance of wavelength diversity. The anomaly around 3i Atlas existed only in aggregate. No single mode, no single instrument could have revealed its full nature. NIRCam showed shape, NIRSpec showed chemistry, MIRI showed heat and evolution. Only by weaving these threads together did the story emerge a halo structured by internal processes, dust arranged by strange forces, and a body far more dynamic than its inert appearance suggested. The halo's layered chemistry only became clear when spectra from NRSpec matched thermal profiles from MIRI. The forward arc only made sense when NIRCam's scattered light aligned with mid-infrared energy distributions. Even the subtle acceleration anomaly depended on the synergy between positional tracking and spectral timing. Every puzzle piece relied on the others. Webb with its precision revealed not just an object but a system, one that demanded models beyond the solar system's experience. The continuing pursuit. As 3i Atlas drifted onward, receding from optimal visibility, Webb's time on the target dwindled. Yet the data it gathered would become the basis for years of analysis simulations and theoretical work. Every pixel, every spectrum, every long wavelength filament became a clue, and the pursuit continued through reprocessing, cross-calibration, and meticulous comparison with laboratory analogues. Webb's detectors had given humanity a new category of relic, an interstellar traveller, whose internal architecture and surrounding halo behaved unlike anything observed before. Through the telescope's golden mirror, the object revealed itself not as a mere stone drifting from a distant sun, but as an evolving archive of geology, chemistry, and cosmic time. The pursuit was not merely instrumental. It was a revelation in infrared. Even as Webb's instruments traced the intricate architecture surrounding 3i Atlas, astronomers understood that no single observatory, not even the most precise ever built, could shoulder the full burden of interpreting an object this strange. The anomaly required perspective. It demanded corroboration across wavelengths, across techniques, across instruments, grounded not in deep space, but beneath Earth's own skies. And so, as Webb's data ignited debate telescopes across the world, pivoted toward the interstellar wanderer, adding their voices to the growing chorus of measurements that sought to refine, test, and challenge every hint of the mystery unfolding in the infrared. The narrative of 3i Atlas expanded outward, carried by observatories that could offer what Webb could not: rapid cadence, diverse viewing angles, broad temporal coverage, and the ability to monitor changes too subtle or too fleeting for a space telescope constrained by strict scheduling. What emerged was a composite vision ground-based and orbital eyes, forming a constellation of inquiry, each revealing a different aspect of the interstellar visitor's evolving complexity. Ground-based optical observatories, the shape of motion. The first to join the pursuit were the optical telescopes facilities like the Canada-France-Hawaii Telescope, the European Southern Observatory's Very Large Telescope, the Subaru Telescope atop Mauna Kea, and dozens of smaller fast-response instruments across both hemispheres. Their role was unglamorous yet essential, tracking the object's precise position night after night, refining its orbit with sub-arc second astrometry. What these observatories found reinforced Webb's disquieting implications. Even after accounting for gravitational influences, solar radiation pressure, and tiny dust loss effects, the trajectory of 3i Atlas remained irregular. A persistent soft deviation mirrored faintly in its shifting halo. Astrometric refinements revealed that the object experienced tiny shifts in acceleration, correlated with the intensity of its dust arcs. When the forward halo brightened, the orbital residuals deepened. When filaments thickened or dispersed, the residuals shifted correspondingly. Though minuscule, these perturbations resisted assimilation into standard models of motion. They suggested again what Webb had implied: internal changes within the object. Structural transitions, compositional rearrangements subtly altered its dynamical profile. Ground-based telescopes also traced faint variations in brightness. These photometric modulations, though easily drowned in noise, displayed periodicities too smooth to be random. Some cycles matched the object's rotation. Others followed longer rhythms likely tied to internal thermal processes revealed more dramatically by MIRI. Spectroscopy from Earth, the missing ingredients. Large terrestrial spectrographs. Keck's Hires, ESO's X-Shooter, Gemini's GENIRS attempted to identify the chemical signatures that Webb detected in the infrared. Though Earth's atmosphere obscured many relevant wavelengths, the data they did capture was startling. The spectral lines expected from classical comets were astonishingly weak. No strong water signatures, no robust CN or C2 emissions. Instead, the spectra showed faint organic absorption features resembling complex carbonaceous residues, along with subtle lines hinting at unusual isotopic ratios. The consistency across instruments supported Webb's claim 3I Atlas lacked a traditional volatile inventory. This absence confirmed that the tail's behavior, the filaments, the forward arc, the braided strands could not emerge from typical cometary outgassing. Ground-based spectroscopy helped rule out the familiar, narrowing the field to the exotic. The Hubble Space Telescope high-precision stability. Hubble, though, aging compared to Webb, played a pivotal role. Operating in visible and ultraviolet wavelengths inaccessible to JWST Hubble, provided images with extraordinary stability and precision. It captured the faint scattering patterns of dust grains, revealing details invisible to optical ground-based systems. Through Hubble's eyes, the halo appeared less like a diffuse cloud and more like a structured envelope, its outer edges displaying gradients reminiscent of weakly bound dust shells. These shells expanded and contracted rhythmically, mirroring the cycles detected by Webb in the infrared. Ultraviolet imaging offered another revelation: trace signatures of photolytic products, chemical fragments produced when ultraviolet sunlight breaks apart molecular bonds. But the distribution of these fragments did not match typical cometary patterns. They clustered instead in narrow arcs ahead of the object, again reinforcing the idea of a forward-leaning anomaly. The ultraviolet data also revealed something unexpected: regions of the halo that appeared shielded, absorbing less UV than their surroundings. These zones suggested dust grains with unusual optical properties, perhaps coated with materials rare in solar system environments. Radio observatories listening for silence. In the background of this optical and infrared pursuit, the radio community attempted to detect thermal emissions gas signatures, or rotational lines from molecules around 3I Atlas. Facilities like ALMA NOMA and the Very Large Array pointed their receivers toward the interstellar visitor. What they found was absence. No CO rotational lines, no ammonia, no methane, no significant outgassing events. This absence strengthened one of Webb's core insights. The halo was not driven by volatile escape, at least not through known molecules. The dust carried organic residues and exotic ices, but if gases were released, they were below detection thresholds, or composed of species that produced no radio signature. ALMA's high-resolution imaging did, however, detect faint thermal emissions from larger grains. These data suggested that some of the halo's dust was denser, heavier, and more thermally stable than expected, a clue that pointed again toward internal processes shaping the distribution. Solar system missions as auxiliary witnesses. Though no spacecraft passed near 3I Atlas, several carried instruments capable of opportunistic measurement. The Solar and Heliospheric Observatory SOHO, Parker Solar Probe, and even ESA's Gaia mission provided peripheral data points. Parker Solar Probe detected subtle changes in local charged particle environments during certain alignments, hinting though inconclusively at interactions between the object's dust and the solar wind. SOHO found faint but measurable signatures in its Lasco coronagraph frames consistent with dust scattering, but inconsistent with classical comet morphology. Gaia refined the object's astrometry with unparalleled precision, confirming once and for all that the trajectory deviations were not artifacts. Each contribution reinforced the same conclusion: 3I Atlas was not behaving like any known class of small body. The cross-instrument synthesis. As data flowed from every corner of the observational community, analysts built a unified model. The model revealed a halo far more stable than a comet's coma, filaments sorted by chemistry, not grain size, thermal patches tracking internal transitions, not solar heating, a forward arc contradicting known dust dynamics, subtle orbital deviations linked to internal processes. Ground-based telescopes confirmed Webb's discoveries. Webb refined what Earth-based instruments hinted at. Hubble provided structure. Radio observatories provided context. Solar missions provided environmental constraints. Together, their observations formed a coherent picture. 3I Atlas was a system, not an inert object. Its behavior emerged from slow, ancient, deeply buried processes, layered histories shaped by environments foreign to our solar system. And across this collective pursuit, a humbling realization spread. If a single interstellar traveler could exhibit such complexity, then the galaxy might be filled with relics equally intricate, equally foreign, drifting silently between stars. Humanity had simply never looked closely enough until now. With each new dataset, with each refinement to the object's orbit composition and thermal behavior, a shift took place not merely in scientific interpretation, but in the deeper intellectual terrain beneath planetary science and astrophysics. The presence of 3I Atlas and the patterns unfolding around it forced researchers to widen their lens far beyond the specifics of this one interstellar wanderer. The anomaly was no longer an isolated case. It had become a catalyst, a lens through which humanity began to reinterpret its assumptions about the kinds of bodies drifting in the galaxy and the environments that sculpt them. The mystery of 3I Atlas was reshaping the cosmic context itself. The first and most immediate implication concerned interstellar object diversity. Before the arrival of Oumuamua and Borisov, theories of interstellar debris relied on analogues from the solar system: comets, asteroids, perhaps fragments of rocky worlds. But the layered, resonant, internally active behavior of 3I Atlas suggested that interstellar space might host categories of objects entirely absent from our local environment. This realization forced astronomers to reconsider the most basic assumption of small-body science, that the solar system's inventory represented a typical sample of planetary debris. If 3I Atlas was a relic of processes that never took place here, if its chemistry reflected worlds shaped in disks unlike ours, in temperatures we never experienced under stellar conditions we've not observed, then it stood as evidence that the galaxy's small bodies were formed under an enormous, largely unexplored diversity of conditions. The solar system was not a template. It was one example among countless improbable variations. The halo, the strange dust architecture, the thermal cycles, the faint orbital deviations, all of these became clues pointing to a broader truth. Planetary systems may routinely produce bodies far more chemically and structurally complex than our own. And interstellar space, rather than homogenizing these bodies, might preserve their diversity, allowing relics of ancient worlds to drift as archives of conditions long vanished. This understanding implied that our models of planetary formation needed expansion. Protoplanetary disks could no longer be treated as uniform structures producing predictable gradients of material. Instead, they might experience chaotic episodes, short-lived heating waves, magnetic instabilities, sudden bursts of radiation that imprint complexity into the planetesimals forming within them. These bodies could acquire layers from different radial zones, carry mixed inventories of ices and silicates, or contain pockets of exotic chemistry preserved in metastable states. The structure revealed by 3I Atlas supported a view of disks as dynamic, turbulent environments, where matter cycles between extremes before settling into stable configurations. Such processes could produce planetesimals with internal architectures unlike anything in the solar system. The implications for exoplanet composition were similarly profound. If planetesimals formed with such complexity, the planets built from them might carry reservoirs of exotic ices, unusual mantle phases, or high-pressure organics that shape their geology in unfamiliar ways. The next implication arose from the tail and the forward arc, the strange dust structures revealing how the object interacted with its environment. If 3I Atlas hosted internal processes subtle enough to influence surrounding dust without visible jets or vents, then it blurred the boundary between active and inactive bodies. It implied that small bodies can exhibit forms of activity far quieter and more regulated than cometary outgassing. These forms might include chemical reorganization, pressure wave-driven dust release, or phase transitions capable of subtly shaping surrounding grain distributions. This realization forced researchers to reconsider the definition of activity. In our solar system, activity is obvious: jets, flares, plumes, tails. But interstellar bodies may experience different forms of evolution, chemical, structural, thermodynamic, that operate far below the threshold of comet-like spectacle, yet still alter their appearance and motion. It also suggested that many interstellar bodies might appear inert simply because we lack the sensitivity to detect their faint signatures. The complexity seen in 3i Atlas might not be unique. It might simply be the first example studied with instruments capable of revealing its secrets. The halo's coherence added yet another layer to the reinterpretation. Its braided filaments and chemically sorted arcs implied that dust motion could be influenced by forces too subtle for classical models to capture. These forces might involve electrostatic gradients, pressure-driven reorganizations within the interior, or even the inherited charge distribution from interactions with interstellar plasma. The presence of such processes forced astrophysicists to acknowledge that dust dynamics are not universal. They depend intimately on the object's history composition and internal state factors far more variable than previously imagined. This realization extended into orbital modeling. If internal processes subtly influence the motion of interstellar bodies, then models used to predict the paths of such objects must incorporate terms reflecting internal mass redistribution and dust-mediated forces. The discovery that the acceleration of 3i Atlas correlated with halo changes implied that motion itself could carry traces of internal evolution, forcing dynamicists to treat interstellar objects not as simple masses, but as evolving systems. Perhaps the most far-reaching implication concerned cosmic chemistry, specifically the endurance of fragile molecules and metastable phases. The presence of delicate carbon chains, partially hydrogenated species, and exotic nitrides in the halo challenged long-held assumptions about molecular survival in interstellar space. Such compounds were expected to degrade rapidly under cosmic ray bombardment and ultraviolet radiation. Yet 3i Atlas carried them in abundance, suggesting that either the object's internal layers shielded them for millions of years, interstellar chemistry replenished them through reactions at ultra-cold temperatures, or the object experienced environments that preserved rather than destroyed fragile molecules. Each possibility reframed the chemistry of the galaxy. If interstellar debris can preserve primordial organics and exotic compounds for such long spans, then the chemical richness drifting between stars may be far greater than expected. These bodies could serve as reservoirs of prebiotic molecules or catalysts for chemical reactions, seeding new star systems with a diversity of materials that could influence the earliest stages of planetary formation. Finally, the mystery deepened into the philosophical realm of cosmic time. The stratified structure of 3i Atlas, its relic layers, its mixed chemistry, its faint internal processes, all hinted that this object had not merely survived, but evolved across incomprehensible epochs. It was a geological and chemical timeline compressed into a single drifting fragment, carrying records of environments long extinct. In this sense, 3i Atlas became more than an anomaly. It was a messenger from eras that predated Earth, a witness to cycles of stellar birth and destruction that shaped regions of the galaxy we will never see. The recognition that such objects wander through the Milky Way suggested that the galaxy is saturated with relics of its own past, fragments of star systems erased by gravitational chaos, collisions, supernovae, and time. These relics drift silently, each containing a story told not in language but in chemistry structure, and the faint signatures of processes still unfolding within them. And in this light, the mystery of 3i Atlas transformed. It was no longer a singular puzzle, but a window into the vast, quiet diversity of cosmic debris, an introduction to a chapter of astrophysics only now beginning. What Webb detected was not an aberration. It was a reminder that the universe is deeper, stranger, and infinitely more layered than Earth's skies suggest. 3i Atlas was not an exception. It was a revelation waiting to be understood. As the anomaly of 3i Atlas unfolded its halo shimmering with stratified grains, its filaments twisting like faint threads pulled through darkness, its interior whispering through subtle thermal beats, its motion bending with the soft pressure of buried transitions, the scientific community realized that the discovery was no longer confined to data. It had become a threshold, a line crossed, a moment when the familiar boundaries of planetary science, cosmochemistry, and astrophysics dissolved into a deeper, older ocean of questions. And at the heart of that ocean lay a truth both humbling and profoundly disquieting. The universe is filled with relics we do not yet know how to see. 3i Atlas had entered the solar system without spectacle. No luminous coma, no blazing tail, no dramatic brightening. It slipped across the heliosphere like a wandering ember of some forgotten forge, its secrets wrapped in a halo too faint for the naked eye. Yet Webb revealed that behind this quiet facade lay a structure shaped by environments foreign to our sun, sculpted across epochs, too vast for human chronology and guided by processes too subtle for the solar system to teach. This single interstellar object had carried with it an entire cosmological history layered evolving unresolved. The philosophical weight of this realization fell quietly at first. In research groups in observatory control rooms in late-night teleconferences, where spectral lines ghosted across screens, scientists found themselves facing a new kind of cosmic narrative. The mystery of 3I Atlas was not merely about what the telescope had detected. It was about what detection meant that interstellar visitors are not monolithic stones, but archives of time, that space between stars is not empty but luminous with the remnants of ancient systems, that the galaxy is not a void but a mosaic of journeys spanning millions of years. Humanity had long imagined the stars as distant, unreachable worlds, but here was a fragment from one of those worlds broken, wandering, but intact enough to carry the memory of its origin. Its halo told of chemistry preserved against entropy. Its internal architecture whispered of environments that alternated between searing heat and profound cold. The dust drifting around it bore isotopic signatures from stellar winds long extinguished. The subtle acceleration written into its trajectory hinted that its evolution was not finished. Every behavior, every spectral trace, every anomalous filament pointed to a traveler shaped not by chaos alone, but by the slow physics of cosmic time. And as 3I Atlas receded from view, slipping once more toward the interstellar gulf, scientists confronted a deeper existential question. If this is what one visitor reveals, what else drifts in the darkness between the stars? How many relics wander silently bearing stories of worlds that bloomed and collapsed long before Earth formed? How many shards of lost systems pass unseen through the heliosphere each century? How many carry chemistries the solar system never produced, architectures no comet displays, or histories so long that human scales evaporate in comparison? The final implication reached beyond the object's chemistry, beyond its halo, beyond even the scientific models assembled in its wake. It was a shift in humanity's sense of cosmic belonging. For if interstellar objects bear the layered signatures of their origins, preserved by time, shaped by collisions, altered by radiation, sculpted by chemical transitions, then the universe is filled not with isolated points of light, but with the debris of countless forgotten epochs. The galaxy becomes a vast drifting archive, and Earth with its young oceans and brief civilizations becomes one chapter among many. In the quiet of that realization, 3I Atlas became more than an anomaly. It became a reminder of fragility, a reminder of scale, a reminder that the cosmos is not a place of stillness, but a tapestry woven from countless migrations of stars, of worlds, of fragments that outlive their birthplaces. Webb detected a halo around 3I Atlas, but the halo was never the true mystery. The true mystery was what it meant to live in a universe capable of producing it. And as the object faded into the deep dark, the unanswered questions settled gently behind it. Questions that would shape decades of inquiry, decades of wonder, decades of human attempts to interpret the quiet, drifting relics that enter the solar system, carrying the memory of other suns. What else is out there? What waits beyond the next visitor? And what secrets lie frozen in the dust between the stars? And now, as the journey of 3I Atlas recedes into the horizon of thought, the narration softens, settling into the stillness that follows revelation. Imagine the object far beyond the planets, again leaving behind the warmth of the sun, its halo dimming its filaments, falling quiet in the cold. The dust that once traced its hidden rhythms disperses grain by grain, dissolving into the vastness, until nothing remains but the memory of a strange, intricate traveller passing briefly through our sky. In this calmer light, the scale of the mystery stretches gently outward. The galaxy becomes a place not only of blazing stars and spiralling worlds, but of countless wandering fragments, silent drifting emissaries of systems long dissolved. Each one carries a whisper of a different chemistry, a different history, a different chapter in the long unfolding of cosmic time. And while the machinery of science reaches for explanations, while telescopes map the faintest rays of ancient light, the heart finds something quieter in the story, a reminder of how small the solar system is and how young. As 3I Atlas fades, so does the urgency of its puzzle. What remains is the steady, reassuring truth that mysteries like this will come again. Perhaps in a decade, perhaps in a century, another interstellar visitor will cross the sun's domain carrying secrets, equally strange secrets, no single telescope, no single theory, no single age of science could fully unveil. And when it comes, humanity will look upward once more, listening for the quiet signatures embedded in its drifting halo. For now, let the image of Three-Eye Atlas settle softly at the edge of imagination, a lone traveller returning to darkness, its layered history intact, its ancient processes continuing in silent rhythm beneath an endless night. Sweet dreams.